Hello everyone. Today we look into this paper called ImageBind from Meta, and this is one of the popular paper that has recently come out. And this paper is about kind of having a single representation space for all kind of modalities. And why this paper kind of have come of now or has become popular now is because if you look into the recent progression in the research community, at least in the computer vision aspect, is how to have a single representation space across multiple modalities. That's the central binding question, and it has kind of led to a huge progress in computer vision itself for all kind of tasks. With the introduction of this clip and audio clip and everything, now you have a single representation space across different modalities. For example, in clip you have this image text pair, in audio clip you have audio text pairs. Now the question comes, can we extend this let's say the single representation space not only for, let's say, two modalities but for multiple modalities, say for 3, 4, 5? It can be done, but the question now comes back to the data. Now if you want to have a single representation space across multiple modalities, you need all possible combinations of the data. For example, you let's say we are taking we are taking audio, image and text. Now for having a single representation space across these three modalities, you need audio image pairs, you need image text pairs, you need audio text pairs. So, and if this increases, the number of combinations that will be needed will increase exponentially. Let's say you also have let's say you want to say depth map images. Now you also need audio to depth, image to depth, text to depth, to kind of map these all modalities into a single representation space. And this becomes a problem because it's increasingly let's increase way faster the number of modalities, the combination of modalities that you will need to train to have a single representation space across multiple modalities. So that's where these paper ImageBind comes up. What it says is you don't require all these pairing modalities to have a single representation or single embedding space for these all. What you can do is you can have just a image representation, image as the anchor representation space, and rest of the modalities can fluctuate. For example, you will just have image to audio dataset pairs, you will have image to let's say text image to text, image to depth. So you just need three combinations of data sets rather than here it goes to 6. So you have kind of increasing the possible number of increasing or kind of decreasing the number of the combination of data set that's required to have a single representation space, which becomes infeasible if you have a multiple, let's say way beyond 5 or 6 to have all combination of data set. And it's also not possible to have a single, let's say all kind of modalities present in a single where you can extract those from. So that's where this image binding approach comes. So you don't need all these modalities at all. You just need all these modalities just paired with some kind of images, where image is basically acting as a binding modalities for all the representation. So that's the main theme of this work. They are saying that instead of having this combination of modalities to get a single embedding space, you need only image paired with the other modalities to get to this the same result, to have a single binding embedding space for all. So how they have to do, let's go into their main results and how, or the work they have done. So as I said, instead of having this all combination, you just need an anchor, image as an anchor, and you need the combinations of all the modalities that you have. And the main way they have done is basically using let's say InfoNC or SimCell loss that we all know of. So they are saying that given a pair of modalities I and M, where I is the image and M is the all the varying modalities where you want a single representation space, they pass it through the both images and the other modalities pass through the encoders to get their representation. For example, qi and ki, qi represent for the image and ki represent for the all the other modalities. And now they are basically using this influency loss, where you are trying to bring this the representation from the image and the other modalities closer to each other and pushing away all the other samples, all the representation of other samples, as well as the other samples of your own domain to be far away. So it's nothing fancy. It's a general well-known the influency loss or SimCLR loss, as you want to call it. And they are bringing these two closer, and rest are kind of pushed apart. And this is not only, let's say, here the image is acting as a modality. You can also have the other way around, where L is kind of calculated with other modalities at the anchor. So LMI. So the loss that has been this whole ImageBind paper has been trained on is very simple. It's using this SimCL loss both sides, and that's all they have done. And they show that using this simple yet very expressive technique, you can have a common embedding space for all of these modalities that you have, rather than requiring a huge combination of all possible pairs of modalities. And as they say, they're using the vision encoder for images, and they are also using the same for the videos. For audio, they are converting or convert a 2-second audio sample at 16 kilohertz into spectrograms using 128 mil spectrogram bins. And once you have got the spectrograms, as usual, you're treating these as images, and then they basically pass this through with the VIT with the pad size of 16 and side 10. And similarly for others. So this is just an encoding steps, how they have used to encode those into the vectors actually. And once you have got the vectors from all the individual modalities along with the image modalities, you just use the influency loss across the both. So this paper is simple yet very efficient, which is kind of open up the doors where you don't need all the let's say possible pairs of combination. You just have this any modalities paired with the images, and you can get a very high results. And we now look into this, some of the results in the table 2. Here they are basically trying to gauge how this text is kind of mapped or mapped to other modalities, even if it is not trained with. So we are, let's say, training with the image on these 5 modalities, let's say image, videos, depth, audio, and IMU. So we have these 5 modalities, and we have all these pairs I to D, I to V, I to A, and I to IMU, and I to text. Text is also there. I to text. Now the question is, how do you map this text to, let's say, the question is how now to evaluate whether this image bind approach works. We need to kind of see how these 2 modalities where it is not paired actually work. For example, we have only paired with everything with the images. Now what about if you test on the text with video, text with let's say depth, text with audio, text with IMU. So that's what we are doing here, to see even if we didn't trained any of these modalities with text, does image, since we are our hypothesis is image works as a binding embedding space, all of these should also perform better. So that's what here, and some of these baselines are basically compared if there exists some kind of evaluation or data sets where the text and the corresponding modalities are trained. So the image binds, let's say, goes to for 54 in let's say depth, where you are just training image with the depth, while the test is on text with the depth, and still image shows much higher performance than if you trained depth images with the text. So it's clearly shows the image image as a binding modality works better even exclusively than just training on the depth text pairs, because of the rich semantic information that it has across multiple from different multiple modalities. Even on this audio, you can see image is fairly good in comparison to the audio text pairs. And here we don't have any kind of a paired data, but still it shows a good performance all across the different modalities. Yeah, so that was the principal aim of this project, to kind of look into how image can kind of work as a central modalities for all central modalities for binding all other modalities across computer vision tasks. Thank you all.